Hey everybody. And we're doing it. Hey everybody, how's it going? So welcome to lesson 2.D. Essentially, last section we went through building functions out of other functions in terms of just the concepts. That's why we're sticking with the arrow diagrams. That's why we're sticking with tables, because that's the general idea behind everything, spelled out right in terms of the ideas. Okay. In these courses and in the future, you might see those concepts later in further other more abstract math classes, but in calculus, mostly we see this type of thing, composite functions, in terms of algebraic expressions specifically. So it's time to start talking about what it means to make expressions out of other expressions if you have algebra. Okay, so this isn't rocket science. 3x plus 2, hey, it's a polynomial. G, here's another function, x minus 4. We can make new functions by adding, subtracting, multiplying, and dividing these functions, right? So, for instance, f of x plus g of x. This is a new function. What's its name? I don't know. You can call this f plus g all of x if you want. And this is just, how to do it, you just write them like that. Okay, before we go on, let me emphasize the connection between this and the previous section. In the previous section, what we did was for each value of x, for each value of x, you calculated the outputs of the two functions, and then you added those together. So for each value of x, they're the same in both cases. This is the value of the output of f of x. This is the value of the output of g of x. But now I can, now I'm allowed to rearrange things just because, hey man, why not? 3x plus 2 plus x minus 4, and you rearrange this and it becomes 4x minus 2. And that is what you get if you add them together. You can subtract them. Why not? F of x minus g of x. You just replace this term with the actual function's expression. You replace this term with the actual function's expression. Instead of g of x, you write x minus 4, and then you get rid of the parentheses. Careful when you're doing this. You don't want to mess up the signs. But we saw this as an exercise in the last, in the first series of videos. So this becomes 2x plus 6. You can multiply them. F times g, all x, I guess. So we'll call this the function you get when you multiply them together. Like, it's not rocket science. We've been building a firm foundation in these ideas for a while now so that we could get to the point where these particular steps didn't require too much explanation. So you just replace the f of x, the name, with the function's actual expression. You replace that, the name, with the function's actual expression, and then you expand. Which becomes 3x squared minus 12x plus 2x minus 8. Which you can simplify even more. 3x squared, no, come on, minus 10x minus 8. Yeah, it's not hard. I'll ask you to do this a couple times in the worksheets, but you know, when it's not too weird. The last one, you can divide them. So f over g of x is just f of x divided by g of x. It's a new function, and actually one interesting thing to note is if you subtract, you get a polynomial. If you multiply, you get a polynomial. If you add, you get a polynomial. What if you divide? If you divide, you don't get a polynomial anymore. You get a new type of expression. If you divide them, you get a rational. Which you knew, because that's how I introduced rationals to you. But anyway, that's where rationals come from. You got two functions, and you do the thing with them. Okay. So before we go any further, let's talk about how to evaluate them, just so that we can get this taken care of. Let's focus. You know what? I'll start. Oh no! I'll start a new one. F of x is equal to 2x squared plus 3x, and g of x is equal to, I don't know, 3x. All right? If somebody says, hey, we're interested in this expression. You say, okay. How do you evaluate this at, say, 4? Note that this is a complicated function notation. This is the function's name, and that is essentially the parentheses with the x in it. So this says evaluate this weird function made of other functions at 4. There's two ways to do it. One, you can either evaluate, well, essentially you just evaluate that and divide it by evaluating that, which becomes 2 times 4 squared plus 3 times 4 over 3 times 4, which is 1632 plus 12 over 12, which is 44 over 12. Hooray, it's a number. Okay, so this is pretty basic. I'll ask you to do some of these, but I believe in my hearts that you know how to do it. You just plug in the number. Or alternatively, you can just write the expression out. 2x squared plus 3x. So instead of doing it one at a time, you just write this expression out and then plug it in for x. It's literally exactly the same calculation in both cases. Sometimes it helps, like say, for example, in this case, sometimes it helps to write out the expression. Here, hold on, let me. You know what? I'm gonna erase some junk. Just give us some space here. Erase. Okay, so sometimes it helps to expand this expression. So if somebody says, hey, evaluate this function at 2, sometimes it helps to write it out explicitly, like we have here, and then cancel it, because you end up with something a little bit simpler than this and this, and so plugging in the value at 2 is easier. 4 plus 6 is 10. As opposed to going f of 2 minus g of 2. So that's 3 times 2 plus 2 minus 2 minus 4, which is equal to 6, 8 minus 2. 8 plus 2 is 10. Regardless of how you do it, you should always get the same number, so it's not a big thing. We have other fish to fry. There's a reason I split this particular topic into its own lesson, and it doesn't have to do with adding and subtracting polynomials. In part because we've already spent quite a bit of time talking about expanding and adding and subtracting polynomials, or rather expressing a polynomial in terms of other polynomials that are added or subtracted from each other. So I feel like we've already spent quite a bit of time doing these particular exercises. Right now we've gone from talking just about polynomials to us talking about functions, adding and subtracting functions, but the lessons are all exactly the same. And right now you guys only really know how to use polynomials, so I'm just gonna leave it there. The big topic, the reason I split this off, has to do with composite functions. So before we get too weird in this, I'm going to give you a little preface about, I'll give you the bare bones explanation, and then I'm going to circle around back and take a longer run at it. Because the way we talk about composite functions is a little bit confusing, and there's a reason we just spent an hour and a half talking about composite functions in terms of arrow diagrams. It's essentially preparing you for this section. Don't worry too much, but here's the argument. 3x squared plus 1, and g of x is x minus 2. How about 4x minus 2? Okay? Then this is a composite function, and this is a composite function. And we talked last time about, we introduced these ideas as composite functions. The idea is first you evaluate that one, and then you evaluate that one. Or first you evaluate this one, and then you evaluate this one, and then the numbers you're going to get are different. So these two composite functions are different from each other. But essentially the way you write them down is using something called the substitution rule, or the replacement trick. I just replaced the x squared in this expression with the g of x expression. Similarly, in this one, I'm going to replace the x in the g of x with the plus 1 minus 2. And then these expressions can be expanded. Anyway, so did that make sense to you? So if somebody tells you to evaluate f of g at 6, now that we have this expression, I can just replace the 6, the x here, with a 6. 3 times 4 times 6 minus 2 squared plus 1, and then calculate that number. You want me to calculate that number? Sure, I've got a calculator. 4 times 6 minus 2 all squared plus times 3 plus 1. 1, 4, 5, 3. Hooray! So the overall purpose of this whole section is to teach you essentially how to start with expressions like that. They're both functions of x. You're asked to do something like that, rewrite it out, which will in turn allow you to evaluate it quickly. Okay? So if that didn't quite make sense to you, if it made sense to you perfectly, fantastic. That makes me super happy. Maybe you don't really need to pay close attention to the rest of the video. If it didn't make sense to you because of how we started introducing composite functions in terms of money, seed, and tomatoes, then stick around. I'm going to bridge that gap. But first I'm going to drink some water. Before we go any further, we need to talk about function notation. And the variable x. Okay? So as you know, when we write that something is a function, we usually go like this. Say if I go 2x plus 1. Okay? The idea being that the name of the function, f, also identifies what the name of the variable is. In this case, the variable is x, and that's where it shows up. Why do we care about the name of the variable? Well, in part, this gives us a recipe called the substitution rule, or sometimes it's called the replacement. Let's see, which one did I call it? I think I called it the replacement rule. For evaluating functions. This expression here doesn't just specify, I know when I taught it to you, I said, this specifies that we want to evaluate the function at the variable x equals 2. Okay. But it does a little bit more than that. If you think about it in terms of the operation, what you're doing is, you see that x in the original expression? You're going to replace, every time you see an x, you're going to replace it with a 2. 2 plus 1. This leads to a number, which you can calculate. Output. Input, output. Okay? Here's the thing. Everybody's super attached to the variable x. But there's no real reason for it. I mean, there's a historical reason for it, but there's nothing special about the variable x. And in your life, you've seen other expressions that have other terms that work as variables that aren't x, right? And so I could, instead of writing it in terms of the variable x, I could just have easily has written it in terms of t. Or I could just as easily have written it in terms of the variable u. But we're actually reaching an interesting point in terms of abstraction, which is, so I've written a bunch of expressions here. This one's just a number to evaluate, so don't worry about it. In fact, let's just set this aside for now. I've written 3 expressions here. All of them involve a variable. The variable's x, the variable's t, the variable's u. Are these the same expression? Are they the same expression? No. Are they the same function? Are they the same function? Well, I mean, let's express this function in a slightly different way. Let's express it as like in terms of inputs and outputs with an arrow diagram, okay? Or even a table. Hey, why not? X equals 1, 2, 3. Our original expression, the output is 3, 5, and then 7. Now, with that one, the variable's name is t. So when t is equal to 1, 2, and 3, the output's 3, 5, 7. And what about this last one? Oh, sorry, it's in terms of u. F of u. 1, 2, 3, 3, 5, 7. So there is a question, which is, are these all the same function or are they different functions? I mean, they're different expressions. They involve different letters, right? But are they the same function? And the answer is, yeah, they're definitely the same function. What do I mean by that? I want you to remember what we said about functions. Functions are kind of relationships between sets of numbers. They're us saying, you give me an input, I'll give you an output. You give me an input, I'll give you an output. And when you compare these function tables, we see that for this input, the output is the same for this one. For the same input, the output's the same. Inputs 5, outputs 2. Inputs 2, inputs 2, outputs 5. Inputs 2, outputs 5. Input 2, output. Input 3, output 7. Input 3, output 7. Input 3, output 7. The tables are exactly the same. The relationship between the numbers are the same. If I were to draw these as arrow diagrams, they would have identical arrow diagrams. Okay? And that means that even though these functions look different, they look like different expressions, all of these functions are the same function. These are all the same function. Which is weird because the variables are different. What makes a function isn't the variable name, it's the relationship between the input and the output. So we can use whatever variable name we want. Well, if they are really all the same, like we argued that two polynomials in one of the first lessons, we argued that two polynomials were the same because if you expanded one, it looked exactly like the other one. So if indeed all of these expressions are the same, if this one's the same as this one's the same as this one, there must be a way to transform between them in a way that doesn't bias towards one variable name or another. And there is, and it's called the replacement rule. See, when we've been using the replacement rule, we've been using it to evaluate the function at specific inputs, right? In other words, I say f of 2, that means replace the variable with the number 2. But here's the fun thing. We aren't limited to thinking in those terms. We can use the replacement rule, apparently, to replace this x with any dang letter I want, or any expression I want. So if I want to replace, if I write f of a, that means every time you see an x in this expression, replace it with an a. 2 times a plus 1. Or f of a triangle. Every time you see an x in your original expression, replace it with a triangle. Triangle is the shape that describes the variable. It's just a symbol, okay? And this is actually a bonkers thing because it really opens up what we mean by a variable. And we're actually going to be using function notation and the replacement rule to shortcut our way into talking about these composite functions. So I'm gonna write it really big here. The variable name is meaningless. It can be switched using the replacement rule with function notation. Function notation is a super powerful tool that just says, hey, whatever you write in this box, write in this box. Okay? So if that's a 2, write a 2 over here. And then that means evaluate the function at 2. If you write an x, write an x over here. If you draw a happy face in here, draw a happy face in over here. Hopefully it means something. Okay? Function notation gives us a super powerful tool. That's the replacement rule, where you just switch out the x or whatever variable is in here with whatever you replace it with. If I switch the x for an a, I just replace these x's with a's. Okay? It's a tool to evaluate functions like we have been, but it's also a tool that lets us do some fun algebraic manipulation, including changing the variable. Okay, so okay, so composite functions. Whenever people give you a function, they're usually going to write it down in terms of the variable x. There's 2 reasons for this. One of them is because we like to think of functions as kind of little atoms that do their own thing. And the other reason is, like I just said, the name of the variable doesn't really matter. So for instance, somebody could be like f of x, where x is the number of dollars, and the value of the function that you get out is the number of seeds. Alternatively, what they could do is they could be like, oh, here's another function. So, hold on. I haven't specified f of x. So they might say f of x is equal to 2x plus 3, where x is the number of dollars and f of x, the number you get out, is the number of seeds. Alternatively, and they might go like x is equal to 4x, where x is the number of seeds and g of x, the number you get out, is the number of tomatoes. Okay? So the variable x can represent a bunch of different things. In a single problem, you try not to make x represent more than one thing, right? But it doesn't matter. The variable, hold on. The function is the relationship between this and this algebraic expression in terms of that variable. It doesn't really, the name of the variable is absolutely meaningless. So if I wanted to, in 2 different problems, I could associate x with the number of dollars in one problem, and in another problem I could call x the number of seeds. That doesn't matter. So it's a little bit confusing. So instead of talking about it like this, why don't we go to let's consider another problem. Buying seeds to make tomatoes. Okay. So in this case, there's some number of dollars, which you're turning into some number of seeds, which you're then turning into some number of tomatoes. And just like in the last case, I want to know the relationship between dollars and tomatoes. So if I want, using the substitution rule, I can get a little bit more descriptive in terms of my variable name. I can rewrite this equation, instead of x being the number of dollars, I can call it the word dollars. F dollars equals 2 times dollars plus 3. And that is equal to the number of seeds. Or alternatively, I could say, hey, if I know the number of seeds, I can multiply that variable by 4, and that tells me the number of tomatoes. Do you see where this is going? So if somebody gives me some number of dollars, dollars equals, say, $3, I can use this function to calculate how many seeds I get. That's 9 seeds. And then I can use this function to calculate how many tomatoes I get. Does that make sense? So this is essentially a procedure that takes that's where I specify some number of dollars, and then I put it in one function that tells me the seeds. I take the seeds, turns it into tomatoes. So I want to write a new expression, a new function that takes in dollars and results in tomatoes. And the way to do that is actually not too bonkers, right? I mean, so if I know how many seeds I have, 4 times seeds, that tells me how many tomatoes there are at the end. And I know exactly how many seeds I have because it's the output of the dollars function. In other words, so that's just going to be 4 times 2 times dollars plus 3. But if I think about it, when I substituted the number of seeds with the output of this function, what I was really doing was I was replacing the seeds with dollars. This whole procedure, just like last time, gives me a composite function. 8 times dollars plus 12. Okay? So, long and the short of it is, if I'm having trouble with this whole composite function thing, sometimes it's helpful to break it down, and instead of doing it in terms of the variable x, rewrite it in terms of more descriptive variable names. According to the replacement rule, it doesn't really matter which variable name I use, and doing so can track me through it. So let's go through what I just told you in a little bit more abstract way. In composite functions, we usually do these things without words. what somebody will do is they'll say, okay, u, that's the output of a function that depends on x. So x is the input, and u is the name of the output. Just like in graphs. And then I have another function, gu, whose output is y. Okay? And the idea is that I'm plugging this expression into this function. I'm plugging one function into the other. G of f of x is equal to y. In other words, x is the input, and then this whole thing is me doing a lot of different things to the number, and then y is the output. So let me do an example to show what we're talking about. This is a purely operational thing. It's not too weird. So if f of x is equal to 3x plus 2, and g of x is equal to, you know what, let's keep this, let's make the variable u. G of u is equal to 2u squared minus 4. Then if I wanted to plug the output of this expression into this expression, I would be writing g, I replace the u with f of x, and that means I replace the u in this expression with f of x. And now I replace this term with this term. 2 times 3x plus 2 all squared minus 4. And if you want to, you can expand. 2 times, let's see, this is 9x squared plus 12x plus 4 minus 4. That's 18x squared plus 24x plus 8 minus 4. So that's 18x squared plus 24x plus 4. Okay? So there's a reason I keep focusing on me talking about the variable name, and that's because in the wilderness, you're not usually given it in such sweet terms. I said at the very start that usually what happens is you're given both functions as functions, both expressions as functions of x. 3x minus 7, and then g of x is 4x plus 3. Okay? So say on an assignment or on a homework, I might give you these two, or on a test. Okay, not assignment or homework. On the worksheets or the tests, I might give you these two expressions and then ask you to write out and expand this expression. How do you do it? How do you even start? Well, the trick here is actually, it's not so weird. What you're going to do is you're going to start by copying out. You're going to look at this f function, okay? The outer function. That's this one here. You're going to rewrite it with the x's replaced by, you know, holes inside parentheses. And then according to the replacement rule, I'm just going to replace the x's in this here with g of x. So this should be g of x. What does it mean? It means that whatever number the g of x function spits out, I'm going to plug into this. So that's step 1. Step 2 is I'm going to replace g of x with the actual expression itself. 4x plus 3 minus 7. So 1, replace the variable, whatever its name is, with the expression g of x. 2, replace replace g of x with the algebraic expression. And then 3, I'm going to simplify. So this becomes 12x plus 9 minus 7, 12x plus 2. There's lots of weird intermediate steps and applications that we could use to talk about these things. But really, there's 3 lessons you got to take from this. The first is that the variable is meaningless. So on the one hand, you can't expect a variable x to mean anything specific. And the second thing is, you can't expect the variable to be the letter x. The variable is going to be whatever letters inside this parentheses. Sometimes it's an a, sometimes it's a square, whatever. Second thing, substitution, the replacement rule. To deal with a function like this, wherever I see whatever I see inside these parentheses here, I'm just going to replace that term with whatever I see in the parentheses here. Sometimes that means evaluate the function. We've done that a bunch of times. And sometimes that means just write g of x. G of x is a stand-in for another algebraic expression, this one. So I substitute that in, and then I expand out. So the long and the short, I mean, the reason I'm not trying to delve too deep into the different variable names and their meanings is because when you're out in the world fighting things, these variable names they're just all going to be x. There's nothing special about x. People just like writing it because it's a cool letter. 3x squared and g of x is equal to x minus 2. All right, so let's try evaluating f of g of x, and then let's try evaluating g of wait, hold on. Okay, you know what we need to start by? We need to start by doing essentially those table calculations that we were doing in the last one, where I say, okay, I have a function, f of g of x. I want you to evaluate g at x equals 1. How do you do that? First you evaluate g at 1, so that's equal 1 minus 2, so that's minus 1. And then I plug that into f. 3 times minus 1 all squared, that's equal to 3. Okay? So let's start with that exercise. I'll specify which values I want you to evaluate, and then you try it. And then I'll work through it myself. So g of f of 2, and then f of g of 3. And then how about, for fun, f of 1, and then g of 2. Okay? So why don't you try evaluating each of these one at a time, and then I'll teach you how to build the algebraic expression. The meaning of the algebraic manipulation comes from evaluating these, and we evaluate these exactly the same way as we would in the previous case. So f of 2, I start by evaluating this thing inside. That's 3 times 2 all squared, so that's 12, right? Now I'm going to plug 12 into my g function. 12 minus 2 is equal to 10. Try it for the others. G of 3 is equal to 3 minus 2 is equal to 1. And then f1 is equal to 3 times 1 squared is equal to 3. Oh, this one's super fun. First I'm going to f at 1. That's equal to 3 times 1 squared, which is equal to 3. And now I'm going to evaluate the outer function at 3. So it's 3 times 3 squared, so that's 27. First I evaluate that one. 2 minus 2 is equal to 0. And then I evaluate the outer one at 0. So that's 0 minus 2 minus 2. All right. Well, that was fun. Let's try doing it. Delete. Let's try doing the algebra. So, how do I evaluate this expression? I'm going to start by writing the f function where I've replaced these x's with the g expression. And then I'm going to replace the g expression with the actual algebraic expression. And now I'm going to expand. Got it? All right. Let's try one more set of examples. 2x, h of x is equal to x plus 4, and f of x is equal to x squared. All right. So, g of h of x, h of g of x, f of h of x, and then how about a really fun composite? How about h of g of f of x? What are the meanings of all these? There's no particular meaning. It depends on context, but you might see things like this out in the wild, and it's important that you know how to operate with them. Okay. So I'm going to replace I'm going to look at the g function, the outer one, and replace the x with the thing inside. And now I'm going to replace that with its actual expression, and now I'm going to multiply it out. Next one. H is x plus 4, so I'm going to replace that x with g of x plus 4, and then replace the g of x with 2x plus 4. I want you to note, just like in the previous lesson, that this expression and this expression aren't the same. There you go. These aren't the same. They're not the same function. So f is some term all squared. It's the variable all squared. In this case, the variable is h. It's named h of x. And then I'm going to replace that with x plus 4 all squared, which becomes x squared plus 8x plus 16. And the last one, I'm going to replace I'm going to look at h of x because that's the outermost one. I'm going to replace that x with g of f of x. Whatever this symbol is, I'm just going to replace the x in my f function with that, plus 4. Now I'm going to look at the g function. That's that one. I'm going to replace the variable in that with the symbol f of x, 2 times f of x plus 4. And now I'm going to replace the f of x with its actual value, 2 times x squared plus 4. All right, so composite functions, evaluating composite functions, and working with composite functions is a big deal. You're going to see a lot of it in calculus. And so getting the basics of how to write them and how to rewrite them and how to manipulate them, it's a pretty important thing. So I'll leave it at that right now. I'll see you later. This is actually the last lesson in this chapter, chapter 5.